semiconductors in band theory. So band theory grew out of molecular orbital theory. I know that's just going to make you love it, right? Or not. It's just a more comprehensive model for metallic and covalent solids, not the molecular solids. So in a crystal, the atomic orbitals of the atoms within that crystal combine and are delocalized over the entire crystal. So in a sense, the crystal is really one very, very large molecule. It's covalently bonded throughout. When those atomic orbitals combine to form molecular orbitals, the lower energy bonding orbitals are occupied, the anti-bonding orbitals are not occupied. So you might wonder why we even talked about molecular orbital theory. Well, one was to understand resonance in organic structures, but another reason is so that we can talk about how semiconductors work, because we have to understand the bonding orbitals and the anti-bonding orbitals. As we increase the number of atoms involved in this molecule, the energy difference between the anti-bonding and the bonding orbitals becomes smaller and smaller and eventually becomes unimportant, negligible. So here we have an illustration. So here we've got one lithium atom. It's got one valence electron in this orbital here. When we combine two lithium atoms, then they each have an orbital, and when those orbitals combine into molecular orbitals, you get a bonding orbital and an anti-bonding orbital. So those two electrons are going to go into the bonding orbital and leave the anti-bonding orbital empty. I don't like to talk about Li3, so I'm going to skip to Li4. So now we have 4 lithium atoms. They're bringing in 4 different orbitals, and we combine those and we get 4 orbitals. We get 2 bonding orbitals and 2 anti-bonding orbitals. The valence electrons fit in the bonding orbitals. And so as you make this larger and larger, the empty orbitals, the anti-bonding orbitals, and the bonding orbitals become closer and closer in energy until they're just really right next to each other. So we call the occupied orbitals, those bonding orbitals, we call those the valence band. And the empty orbitals, the anti-bonding ones, are called the conduction band. And I envision these as being a bit like a highway. So this part of the highway is occupied. This is full of electrons. This one's empty. Okay, it's like you've got this nice wide shoulder on the side of the road, and you're in this traffic jam, and you look at that shoulder and you're like, man, I wish I could drive over there. Why don't you drive over there? Some of you maybe do, but I haven't seen you do it. Yeah, coming home from Vegas, that is a nightmare. And then, yeah, people do all kinds of crazy things. But why don't we do that all the time? It's illegal, right? And if a police officer sees you doing that, you get pulled over and get a ticket, right? And your insurance rates go up, and there's this cascade of bad things that happens. So there's this thing that prevents us from doing that, right? What if it wasn't illegal? No consequences. Everybody would do it, right? Of course, then it wouldn't be empty, and then we have other problems. So electrons become mobile when they move from the valence band into that higher energy, empty conduction band. So you're on this freeway from Las Vegas to Los Angeles, right? And it's jammed. It seems to always be jammed. And you're just stuck in this stop and go traffic, and there's that empty shoulder, and it's so tempting. If there's no gap in energy, if there's no consequence to going over there, no cost to you, you're going to do it, right? You get over into that empty shoulder, and you can just move. And that's what the electrons do. The valence band is just stop and go traffic, nothing's moving. Stand still. They move into the conduction band that's empty, and they can move freely across the surface of the metal. So metals do this. Metals are good conductors of electricity because the electrons can get into that conduction band because there's really no difference in energy. There's no penalty for driving on the shoulder of the road. This also provides thermal conductivity. So those electrons are mobile. Electrons have kinetic energy. When the kinetic energy of the electrons can spread throughout the metal, that conducts heat as well. In a semiconductor, there is a small energy gap. In an insulator, there's a large energy gap. So here, big consequences for driving on the shoulder. Like, you might actually get arrested and thrown in jail, right? So that was like, no way am I going to do that. And this is maybe, a $50 fine. And you're thinking, heck yeah, it's worth $50 to get to where I'm going faster. So this is a small energy gap. So some of these electrons do make it into the conduction band, and so the semiconductor conducts electricity a little bit. The insulator doesn't, because that gap is too big. It just is not going to conduct. All of these electrons are stuck down here. The conductivity of semiconductors is temperature dependent. If you increase the temperature of the semiconductor, then more of those electrons are able to get into the conduction band and the conductivity will go up. So that's really useful. You can use semiconductors to make digital thermometers, right? Because as the temperature goes up, the conductivity increases. So you've got a battery and you can measure the conductivity and that'll give you the temperature. So this is called the band gap. It's the gap between the bands. As you move down any column of elements, the band gap decreases. Here we're looking at group 4. So carbon in its diamond form has a band gap of 5.5 electron volts. It's an insulator. That's a big difference. It's just not going to conduct anything. Silicon, next down, 1.11 electron volts. So that's sort of it's small enough that it can conduct, but it's still a significant gap. Germanium is also a semiconductor. Tin, now this is a much smaller, 0.08 electron volts. That's small enough to be considered a metal. And lead has no band gap. So as we go down, we see that metallic character increases. That coincides with the band gap decreasing. Any questions? You can control the conductivity of semiconductors not only by varying the temperature, but also by doping them. So a doped semiconductor contains small amounts of impurities. These are either going to result in extra electrons that are in the conduction band or in a deficiency of electrons, which creates holes in the valence band. So let's talk first about the N-type. N-type semiconductor has extra electrons in the conduction band. So the electrons don't fit in the valence band. They have to be in the conduction band. And so then it's going to be more conductive than an undoped semiconductor. So if we take silicon, silicon's in group 4A. It has 4 valence electrons. If we mix a bit of phosphorus in with it, phosphorus atoms have 5 valence electrons. So now this one extra electron from the phosphorus is not going to fit in the valence band anymore. Every phosphorus atom that's in there is going to have 1 electron in the conduction band. The more phosphorus you have in there, the more conductive it's going to be. So those electrons are mobile and they'll carry the charge. This is called N-type because what's carrying the charge is the electrons, and the electrons are negative. So negatively charged particles are carrying the current, and so it's an N-type semiconductor. You dope it with something that has more valence electrons. A p-type semiconductor has electron holes in the valence band. Okay, so let's go back to the highway. So you're on this jammed up highway, and what if an alien spaceship came through and vaporized all the red cars? That would leave some holes, right? You'd be getting rid of some of the cars, and now the car behind the hole could move up, and the car behind them could move up. And it wouldn't be super fast, but you'd get some movement going on, right? That's what's going on with a p-type semiconductor. These are doped with a substance that has fewer valence electrons. So we use gallium to dope silicon. Gallium only has 3 valence electrons. So that leaves a hole in the valence band. The electrons can move into that hole, creating a hole behind them. And so you can think of it as the electrons moving or the hole moving, right? The hole acts like a positive charge, and so it's called a p-type semiconductor. Silicon chips, which are at the heart of most electronic devices, and probably most of us have an electronic device of some kind or another with us today, they contain millions of p-n junctions. So these are junctions where a p-type and an n-type semiconductor meet. And those junctions can act as diodes. A diode is an interface which allows current to flow only in one direction. They can act as amplifiers, taking a small current and changing it into a larger one. And that gets into the whole business of electronics and electrical engineering, which is also very interesting, but not the topic of this class. Any questions? Do you know why the area around San Jose is called the Silicon Valley? I think it's really several reasons that are kind of dependent on each other. There's a lot of silicon naturally occurring there, and big computer industry has grown up there, and they're making these transistors which require silicon. Okay, so we should be able to answer a question like this. Which element would you dope into germanium to create a p-type semiconductor? So the P in p-type stands for which word? Positive. So this is a positive thing moving. Electrons are negative, right? So we have electrons and we have holes. Electrons are negative, the holes are positive. So a p-type semiconductor, we need to make holes in the valence band. Do we do that by adding more electrons or fewer electrons? Fewer. So what we want, if we want a p-type semiconductor from germanium, what group is germanium in? It's in group 4A. Thank you. You guys. Okay, group 4A. So if we want something with fewer electrons, we want to look for group 3A, right? So 3A, we've got aluminum, gallium, indium. Oh, there's indium. So indium is in group 3A. So that's going to have 3 valence electrons. We dope that into the germanium. There's going to be some empty holes in the valence band. So that's our answer right there. Tin is in group 4A. If you dope germanium with tin, what would happen? Nothing in terms of the conductivity because it's the same number of valence electrons. Arsenic is in group 5A. So what kind of a semiconductor would that make? The other kind. Ntype. That would give you an Ntype because it would have extra electrons, and so that would cause there to be electrons permanently in the conduction band. Questions?